No, too deep. It's a good job I've got my wellies on. I'd have got my feet wet then. From earliest times, people have preferred to keep their feet dry if they could. That's why even a stream like this generally had some way of crossing, stepping stones or a bridge. And quite often, the bridges were very simple, just a big stone or a bit of fallen tree. It just had to be long enough to reach from one bank to the other and strong enough to take the weight of a person. The only trouble with bridges like that was they couldn't reach over anything very wide and they couldn't take very much weight. Now that was a problem, and for a long time, nobody could think of a good answer. It was the Romans who found an answer, and their answer was the arch. They built a framework to support the piles of stones that would form the arch. Without this framework, the stones would fall into the river. But when a large wedge-shaped stone was fitted in the center of the arch, then the structure became strong and steady and self-supporting. The center stone is given a special name, the keystone. And here is an arch bridge crossing quite a wide stream. It takes my weight very easily, I'm glad to say. Now, if we look at the ends of the arch, you can see that they're set into very firm foundations. And if we come back to the middle, here, right in the center, locking the whole thing together, is the arch keystone. This is the River Severn, flowing through the Iron Bridge Gorge in Shropshire. And in the 18th century, this was a very busy place to be. There were iron and coal industries on each side, and lots of people working in them. So the river was being crisscrossed all the time by boats carrying iron and coal and people. Now, at certain times of the year, the Severn can be a very dangerous river, so people thought that a bridge would be a good idea. And since there was a lot of iron around, they thought it would be best to have a bridge made of iron. So they built one. This one. Iron Bridge is a single arched bridge, with the top of the arch about 28 meters above the river. It was built high so that the sail barges could get underneath. The bridge wasn't made of solid iron, that would have been too heavy. It was made with an iron framework. And that framework is supported just here and at a similar place on the other side of the river. Now, if these foundations weren't firm, then the bridge could move. It would be unsafe. Well, this bridge is safe, although not for our modern traffic. For this is the very same iron bridge that was erected in 1779 and opened on New Year's Day in 1781, over 200 years ago. The first iron bridge in Britain. These young scientists are testing the weight-carrying abilities of their own bridge designs. In fact, these boxes fitted tightly together make a very strong bridge, difficult to collapse. Not at all like this bridge. The card only makes a good bridge when it's folded. There's still the same amount of material in the bridge, but now it's half as wide and stronger. Even fragile plastic straws will support a large weight when the straws themselves are fitted together and bent into an arch. This is the Clifton Gorge near Bristol. For some time there had been talk about a bridge to cross the gorge. The first design was for a stone bridge, but it never got started. Competitions were held for a new design. This one was from Thomas Telford. A man called William Armstrong produced this plan. And a Bristol designer, William Hill, came up with this one. The competition was won by Isambard Kingdom Brunel. Brunel worked on a number of projects, but his most famous was the Clifton Bridge. He died before it was finished, and the bridge was eventually opened in 1864, 5 years after his death. The design of the Clifton Bridge is quite different from the one at Iron Bridge. That one stands on an arch. Clifton doesn't stand, it hangs. It's suspended from iron chains which cross the gorge between two towers. The bridge is called a suspension bridge. In fact, the chains that hold the roadway are not the ones originally ordered by Brunel. Those chains were sold when the first building project ran out of money. These chains were saved from another Brunel bridge that crossed the Thames in London. The chains are held firm on each side of the towers, deep underground on cast iron plates, which are buried in bricks, which are set in cement, which are held in solid rock. So they're safe enough. And they need to be, because the chains are taking the whole weight of the entire bridge. And that bridge is about 80 meters above the bottom of the gorge. And that's a long way to fall if those chains give way. One of the problems found with suspension bridges was their behavior in strong winds. These young scientists are using a model of a suspension bridge to find how a real bridge might behave in very windy weather. It's only a model, of course, but movement like this really can happen. It happened to the Tacoma Narrows suspension bridge in America. Scientists commonly use models to test the strength and safety of a whole range of structures. How many of the supports on a cooling tower or tower block can be removed without the structure collapsing? This experiment is to find how materials from a volcano can be redirected to cause the minimum damage. If flood barriers can be sited and built properly, then scenes like this could be prevented. But what does make the best flood defense? That's where design and experiment are important. That bridge is safe enough. It was carefully designed and thoroughly tested, and that's true of almost everything in our modern life. Things are carefully designed, then experimented on, tested and improved until we can be confident that they're safe. Big things like tower blocks, aeroplanes, great bridges, and small things too. We can rely on them. They are safe systems. Well, time for lunch, I think. Oh, look at that. Designed, experimented on, tested and improved. I don't know. Paper bags are supposed to be safe. Oh. You'd think they could make something more reliable than that. These young scientists are working on the very problem, how to make a better paper bag. The seams of the bag, the overlaps, will need improving and testing. Perhaps the pastes can be improved. And maybe the bag could be made with better and stronger materials.
Well, I think we've come a long way here, haven't we? This is one of the first paper bags that we have made. Now I will test it. See what I mean? But look at this one. Isn't it smart? Isn't it lovely? Look at the joins and the seams. I think we've got the winner here.